So I will stand up and give you 5-minute warning after 20. So welcome back, everyone. I think we need to press on with the remainder of this session. And it's my pleasure to introduce Vladek Minor, who will give a discussion on a very exciting new development where there is the possibility of having a significant repository of raw data sets for inspection and doing all sorts of interesting things.
Thank you for introduction, for inviting me here. The title is here, and I have to rush, so I will not explain each slide because I understand that they will be somewhere on the network as a raw data of the meeting. We got funded to create integrated resource for reproducibility in macromolecular crystallography. This is the name of that resource. And what are the goals? Develop tools for automatically extracting and curating diffraction images and associated metadata. Create a web-based system for semantic searching, analysis, and data mining of appropriate subsets. And I would like to underscore the word semantic, not develop tools to automatically validate, preprocess, and score diffraction images. Creation of repository for diffraction data that did not yield an X-ray structure. I think that this is very important. And set up a pilot resource incorporating the tools developed in AIM 1.4 to collect a test set of data for development of tools and algorithms. Yes, you have to have large amount of data to really check if everything works. Because what works on the 19 BM BIM9 not necessarily works on 19 ID BIM9. Yes, despite of the fact that it's run by the same people. Yes, software knows about that, but you have to use software which knows about it. But what is the real goal? The real goal is to do protein crystallography or even structural biology with speed and finesse. And this is the real goal. And protein crystallography is very important. And this is a slide from Hiroshima Shinkansen station. And it's advertisement of one of the Japanese pharmaceutical, not big pharma, small pharma company. And as you see, protein structure is something which at least stop people in front of that poster. And they hope that somebody will find somewhere the name of the company. What is the current situation with structural biology? That we have here everything automatic cloning, high throughput automatic expression, so on. And the only thing which is missed is automatic paper writing. Yes, and some people are saying, oh, we could produce a lot of paper, but our bottleneck is this automatic paper writing. And indeed, if you compare structural genomics, where people had to deposit immediately after structure was refined, with classical labs, in case of structural genomics, the time between data collection and deposition was around 100 days. And it didn't depend too much on resolution. And And in case of the classical lab was around 600 days. So it's almost 2 years delay. And this almost 2 years was obviously spent on follow-up studies, which not always were done in structural genomics, but not only on follow-up studies. And even in structural genomics, which supposed to be high throughput, the time between deposition and publication was sometimes 8 years. So at least it may be we had high throughput, but we were not very fast in producing the paper. And why is that? Because what is the real bottleneck? The real bottleneck is data is not information, information is not knowledge, knowledge is not understanding, and understanding is not wisdom. And at least we should have some knowledge to produce paper. So we really we are somewhere in that place. We hope to be somewhere in that place. And now, the real question is, what experimenter knows about data collection? As you see, very little. Yes? And this is the real deposit from PDB. Or you may have some numbers full of wrong information, because blue eyes cannot integrate data. R-merge is, because of that we do not have R-merge, I may say. And it was single wavelength experiment, but it was mud. Yes, mud single wavelength. It's very, very interesting things. The solvent content obviously was not known, despite of the fact that we can easily recalculate it. In fact, to fill all this information about the beamline or about home, you need, and in case of the beamline, you need two things. The date of, you need only the date of experiment. Yes? And the beamline. And everything else should be in the database and should be forwarded automatically to the deposition. Obviously, PDB does not have resources to do it. Yes, it's impossible. It's a real task. And this is one of the goals of our project. Now, something which is not very obvious. If you compare the R3 versus resolution for PDB deposits which have the highest number of nulls and the lowest number of nulls, you have very significant correlation over all resolution. So it means that you have a depositor who knows something, or you have depositors who does not know too much. Yes? So this is very, and I think that we made 20 nulls of less or 50 nulls of more. So this is the difference. I do not remember. I mean, it was several thousands of data sets created on that, and we didn't look at the particular. And you see that we are talking about synchrotrons. The question is where we should collect data. Yes? We should collect data, or at least I am collecting data on beamlines on which I am most successful. Yes, some of beamlines I tried once, and I never came back. Some of beamlines I tried 3 times, and I decided not to go back. So it's very, very interesting plot. I mean, most of these plots are published. And you see that what you see here is that in the years 2011, 2013, the most successful overall beamline, I mean most successful in the sense of the most deposits collected in that time, was NSLS X29A. Yes, they were most productive. You see, they had detector, which many people call obsolete. The company went bankrupt, and NSLS was closed as an obsolete synchrotron. Yes? So we are cutting things which are most productive, and we keep everything else. In case of anomalous data, SAT-MAP structure in the same time. APS 19ID is the most productive, and X29A is second. Shanghai synchrotron is third. Now, if you will look on newer data, Shanghai is first. Yes. And now you may see that various colors describe you bending magnet, insertion device, CCD detector, pixel array detector. That in fact productivity does not depend on all these things. Yes? What we really have is little irrelevant. Yes, and you may say, okay, it depends on users. It's absolutely true. It depends on users. But users are like me. They are going to the beamlines on which they were successful before. And once they are successful, they do not want to go to other places. Remember that the most expensive, that protein crystal is the most expensive things on the earth. It's much more expensive than any, by volume or by weight, than any diamond. Yes? So you see that if we are going somewhere, this is only 15 beamlines. When we are going somewhere here, or it's really here, we have 125 synchrotron beamlines. These beamlines are really wasting your crystals. And you see that this is very, very important. In 1997, I became involved in Sector 19 at APS. And before, it didn't work too well. And Paul Ziegler was supposed to be first external user of the beamline. And he had, I forget his name, he had a very funny postdoc who called me 3 or 4 times before they went there, and he was asking me how good data this beamline produces now. And I said, fantastic, you will be very happy. Yes, I answered 4 times. They came, and Andrzej asked me and Zbyszek to be present. I mean, this was really the future of that beamline, depend on this one trip. And after 1 hour, the same guy came to me, really angry. He was almost mad and said, Wladek, why you didn't tell me that this beamline produced such a good data? And I said, I told you that 4 times. Yes, but you were not convincing enough. So you see that this is how important it is to have success. And now, let's look into the number. Diffraction experiment is the last experiment before deposition to PDB, if successful. Yes? Many beamlines claim that the data set can be produced in 2 minutes. Sample can be changed in 10 minutes. So every 4 minutes we should have data set. Let's give them 2.5 more time for waste. So we should produce every data set in 10 minutes. So 6 data sets per hour, 144 data sets per day. Let's say that only half of the year the synchrotron is working. We should have 25,000 data sets, not per day, per year. So it's 2.5% of the PDB, entire PDB. We have 125 synchrotron beamlines. So we should, in 1 year, we should produce over 300 PDBs. And we don't. Yes, we produce much less. So our efficiency is really 0.3%. So the goal of our resource is the real goal, how to increase efficiency of every beamline. So we would like to do and this is, I'm sorry, you do not see that this is the web page of our resource. And we have, as of yesterday, over 2,700 data sets available for users. And we stop to push for more data sets. I mean, we are accepting data sets. And we should have 3,500 in 2 months, roughly. But because size is not a problem. Yes? The size is not a problem. And we have some limited, we extracted some metadata, not all metadata, and we have some limited search through the database. The metadata will be in the database, so you will be able to search, and you may try that very fast, and play with the data, or reprocess the data. At that point, it does not exist yet. But every data set or every diffraction experiment will have enough metadata to reprocess that at least by 2 packages. So we will start, obviously, we'll start from HKL. We will have the dev site for each of them, and people will be able to reprocess. But what is really interesting is not to give people ability to reprocess. Yes, this may be very, very interesting, but what is more interesting is to do the data mining, to search through the beamline, to check how the beamline change with time. And you see, by looking into raw data, you may detect whether the cryostream on the beamline worked well or not. You can detect whether what has been changed in the frame format and warn people. And you see, people had, on one synchrotron, people couldn't process data for half a year before I got the data. I mean, they could process. They process using some packages, and I was getting information that HKL couldn't process that, but some other packages can process, but we cannot solve structure. Yes, and it happened until I got first data set, and it was math. My friend started to transmit the data in the half of the first wavelength. I have sent him the model. Yes, and I didn't have sequence. But this was very high resolution data. What was the problem? Very simple. They put new detector as a test. And they move the old detector 45 degrees on top or on side. Yes, and 2 theta was 45 degrees in the header. And if you are blindly reading headers, this is what may happen. if you process data not looking at the diffraction images. This is what has happened. And you see, I do not like, to tell the truth, I do not like automatic processing. Yes, I do not like automatic processing, but because processing takes 1 to 2 minutes. And when we collect data now at APS, sometimes it's very easy to get synchrotron time, you know that. Yes, no. Sometimes we collect on 5 beamlines in parallel, one group, and still we process more or less by hand. So this is the home source. We have 170 images from the home, or not images, but experiments from home sources. And here you may see R3 versus resolution. R3 as taken from PDB and resolution. And you see that at home resolutions are more or less the same. Yes, because at home people are using crystals with diffract better. And here, if you will go to particular set, you may have the image, the things from PDB, and because these are, I have chosen CSPID data or Seattle data, you may have access how you produce protein and how you crystallize the structure. And you see, we look briefly on this, and it's clear that some people, judging on the first name on the position, have problems with cryocooling. Yes, that you can associate the name of the person with a problem with cryocooling. And problem of diffraction quality, and diffraction quality is quite often strongly degraded by not paying any attention to cryocooling. 20 years ago, there were many workshops about cryocooling. Now you do not have workshops. People do not know how to put crystal into capillary, and they do not examine the crystal in room temperature. Yes, and they do not pay any attention because everything became high throughput. And high throughput not necessarily means high output. These are two different things. So you have the access to all information, and if you have a metal, you have the access to check my metal. Yes, when we have a server which checks if metal is correct. Again, in PDB, quite often you have structure factors, but the structure factors do not have anomalous signal, despite of the fact that we could tell more about metal or about some atoms if we would have anomalous signal. And the number of suspicious metals in PDB is, or the fraction of suspicious metals, is growing. We are not going down, we are going up. Again, we didn't examine this data carefully. So some of them may be okay. Yes, but this is just without estimation. And here is beamline 21G, also at APS. And we have 180 diffraction experiments. So we can say something about this beam. And we are in the process of analyzing. Yes, the goal again is to do optimal data collection. And you see that the data collection now is very far from optimal. And you see the image and few weak spots. So what is your conclusion? It's difficult, weakly diffracting crystals. Is it really true? You are looking at the data, you have one of these low-resolution spots which have 45 photons. Yes? With Pilates it measured photons. Yes? The data were collected 0.02 seconds, 2,500 data sets. So what 0.02 seconds, and the argument was that if we will average, we will get the same. Yes? Guys, I think that the person who stands behind that idea should patent this idea. Billions of dollars behind the patent. Yes? This is the picture, which is 10 times underexposed. And this is real picture. What would you show to your mother-in-law? Yes? Where are the money? Here. 2 lenses. Yes? 1.2 and 1.8 brightness. One is $2,000, the other one is $360. It's the same lenses, the same Canon lens. Yes, the difference in brightness. Why do we need synchrotrons when we do not need intensity? Yes? We should stop construction of the new beamlines. We shouldn't think about the brightness of the beamline. Why? When we have just average. Now, another way, not related to that, but very important thing, is that these images are a great resource for people who are developing software. And not only processing software, but refinement software, because you can get, from raw data, you can get more information. And you see that this is my group, 21 ID, and you see here, they are collecting data, but they are really looking at the map, yes, because we know this beamline, so we can process data very fast, and we can get maps very fast. And in fact, recently, when we are at the synchrotron, we use more wet lab than beamline, because we are planning next experiment. Yes, we are soaking at the synchrotron. Yes, and it's useful if you have completely database control beamline. But you see that the real problem is that at that point, there is only one step to the big brother. And this is my lab. And you see that last week, I mean, it's little older, but I put that because I'm getting these reports every Friday evening. And you have a lot of data sets processed because we just collected data. We just came from the synchrotron field. And you see the amount of data sets which are processed by some people after the data set, and she's working on 13 structure refinements in the same time. Yes, in the last week. So you can really look what is going on. Before, the week before, you would have a lot of this. Yes, not a lot of data processing. So it changes. And 2 months later, you will have a lot of kinetic assays and thermal shift. We do not have full spectrum of biomedical studies. But I very strongly recommend to use the database, not really to track people, but to find where is the bottleneck, where is the real bottleneck. And this resource, this award started June 1st, so we are really at the beginning of that. We were somewhat prepared for that. Yeah? So you see that this, we had 1,000 experiments before it started, just a preliminary study. And you have a list of people in my lab who were involved in this project. One of these people is here. And in yellow, there are people who have primary responsibility in this project. Unfortunately, one of them left for Google. And this is the third person from my lab who left for Google. So I think that I should get some grant from Google, just at least for educational grant. And you see, I would like to thank all people who are not in this project, but with whom I discuss a lot. And one of them is here. And you really, I said that this grant started 2.5 months ago, but it wouldn't be possible with all efforts of structural genomics. Yes, and this is quite often disregarded. Structural genomics is disregarded, but we have learned enormously, and structural genomics really, and you will see that in 5 or 10 years from now, that it really revolutionized structural biology. Okay, I am emotionally involved, and you see that, but it's really, and obviously everybody is biased, but it's really true. Thank you very much.
Thank you very much, Vladek, for a very stimulating and interesting presentation. What I might take from that is the notion that where we're concerned with metadata, we don't just want to collect metadata just as we collect everything else. It has to be intelligent metadata, and it has to have that semantic meaning to it. Time for 2 quick questions, perhaps.
Vladek, thank you for your nice view and your nice protein diffraction database. And you mentioned that there were actually 2 packages that for which you had enough metadata to get the data processed. And later in your talk, you mentioned I don't like not looking at images. So is there a contradiction in there? I mean,
no, I like to look at images.
No,
yes?
you don't like if people don't look at images.
No, I do not like when people do not look into images.
No,
yes?
But that is...
And you see that dev site, so-called dev site file, and what you have in HKL, is enough to process data set, almost blindly. Under one condition, that this dev site is correct. What I can tell you that the only dev site which is really updated and correct is 21 and 19, 19 and 19 ID and BM and 21 BM. Because we are collecting data every 3 months, and we are looking if these dev sites are correct. And if they are not correct, I am making a help. Yes, over there. And Andrzej is my friend, so I can make a help easily. Yes, it's very difficult to make a help to somebody who you do not know and who does not like you. Yes, I can make a help, but the result is 0.
Kamil Dziubek, Lens, Florence. Thank you for showing us that collecting the metadata is not idiot-proof. But I was just thinking, we have validation tools for the data. We have CheckSIF for receive files. You cannot put bluntly no information, like you, so as no information. If you put like a question mark in place of the lattice parameter, of course, it rejects with a alert. Do we? And let me pose an open question. We need a tool like a validation tool for consistency and for integrity of metadata.
Yes, absolutely. Absolutely. You see that, I mean, the question is, what are the metadata? What is there? Just to reprocess the data, it's a minimal effort, almost minimal effort. Because I can very fast, by myself, I can very fast process this 2700 data set. Yes, I can. This wouldn't be a problem. Because they are coming from few beamlines only, and few home sources. The problem is that when you are getting something from the beamline which your program didn't see before, it sometimes requires a lot of correspondence. Yes, and people think that everything is in the header, and it's really not. Yes, and people have, the real problem is that people have very low standards. Yes, that they are getting 4% are merged, and they are saying these data are great because it's 4% are merged. If you really put a lot of effort, you may get 1.5. But who cares about R merge? Yes, the best way to improve R merge is divided by 2. Yes, it's unweighted statistics. You can do anything you want. What you really need is to extract anomalous signal. And you see that for that reason, the difference between 19ID and the next beamline in anomalous data is, when we are using anomalous data, is 2 times. And in fact, 19ID has, if you were looking for SAT and growing of SAT experiments, 19ID was absolutely the best. And part of that is because it was structured genomics, and in structured genomics we use many new structures. But what I found that now people are doing follow-up studies using SelenoMed, just because it's easier than molecular, that it's really not molecular replacement, but Fourier, by doing Fourier on the structure which you already know, and you do not have any bias.
So can I suggest that we should develop that further in informal conversation later? Thank you again for a brilliant presentation.